Again, it's a red stick.
What is going on, guys? Welcome back to the Algorithms and Data Structures tutorial series. In today's video, we're going to talk about self-balancing AVL trees. Now, in the last video, we talked about binary search trees and about their average case runtime complexity, which is logarithmic, provided that these trees are balanced. Now, we also talked about what happens when the trees are not balanced. When they are unbalanced, we end up with a linear runtime complexity, or can end up with a linear runtime complexity. So in this video, we're going to take a look at self-balancing trees that rebalance themselves in logarithmic time, because when that is possible, we always have a balanced tree. The rebalancing itself is logarithmic, so everything we do, inserting, finding, deleting, is or can be done in logarithmic time. And today we're going to talk about AVL trees, which are the first kind of self-balancing tree that we're going to look at. So let us get right into it. So let us talk about the basics of the AVL tree. Now, AVL is essentially just a combination of the two last names of the founders, of the inventors of the AVL tree, so nothing that has a deeper meaning here. And essentially, the AVL tree is based on a so-called balance factor. And this balance factor is calculated by the height of the right subtree minus the height of the left subtree. So this is what the balance factor is. So let's say we have a simple node here, and we have a left child and a right child. Now, if we want to calculate the balance factor for this particular node, what we do is we get the height of the right subtree, which is obviously 1, and then minus the height of the left subtree, which is also 1. So in this case, the balance factor would be 0. So it would give this node a weight of 0. Now, if we have one more node here, we would have a height of 1 here, a height of 2 here. So 1 minus 2 is minus 1. And this node would have a balance factor of minus 1. So this is how we calculate the balance factor. If we have 2 here, 1 here, the balance factor would be 1. Now, what we're trying to do here is we want to have each node being balanced. And balanced means that the balance factor is either minus 1, 0, or 1. If we have a difference of a maximum of 1, we accept it as balanced. But if we have a difference of larger than 1, we don't accept it as balanced anymore. So in this case, it's balanced. In this case, it's also balanced. In this case, it is no longer balanced, at least not the subtree here. But for example, this would also be balanced here. But the moment that we have 2 more childs somewhere like this, is no longer balanced, because first of all, we have a height 3 here and a height 1 here, so we would end up with minus 2, which is not allowed, of course. The absolute value is larger than 1, the difference is larger than 1. But even if we had something like that here, it would not be possible, because yeah, you could say here we have 2 and here we have 3, so the balance factor of this node would be minus 1. But the problem is, if we look at this node here, so this node, the first node, the root node, would be balanced, of course, so this one is balanced, but this one is not balanced, because if you look at it, you have a tree of the height 2 here and height 0 here, so you would end up with minus 2 as well. So we want each node to be balanced, and if it is not the case that all nodes are balanced, the whole tree is not balanced. So an unbalanced node can happen also somewhere deeper in the tree. You could have a perfectly balanced tree like that. I don't know. So these are actually balanced when you look at the root node, of course. So you can continue on and on forever. And if you compare the two sides here, the heights of the subtrees, you would end up with 4 minus 4, which is 0 and totally balanced. So the root node is balanced, but this node is not balanced because we have 3 and 0, so it would have minus 3, here we would have 3. So the absolute value is larger than 1, and thus these sub trees are not balanced. And for a balanced tree, we want all the individual nodes to be balanced, because why is this the case? Let's say we have, again, this tree that I just plotted here, something like that. Our goal is to end up with a logarithmic runtime complexity. And if only this node is balanced, yes, I'm having the problem size with my first action, but then I'm ending up with a path and I have linear runtime complexity again. So I want to always roughly have the problem size with each step. This would be log 2 of n, or big O of log 2 of n, no matter what happens. So this is our goal, and now we're going to take a look at how to do this. Now the question still remains, what are we going to do in order to balance these trees, in order to rebalance these trees? Let's say we find unbalanced trees. What can we do in order to rebalance them, and how can we do that in logarithmic time? Now in order to answer that question, I have prepared 4 cases here, case A, B, C, and D, that are all unbalanced trees with a balance factor of either -2 or 2. And we're going to look at how to rebalance these because all of those need a different solution, kind of different solution at least. Now let's look at case A. Case A is a very simple case. We have a -2 balance factor, which means that the left subtree has a height that is 2 larger than the right subtree. So in this case, we have a height of 3 here, and we have a height of 1 here. Thus, we have a balance factor of -2. And the question is now, how can we rebalance that tree so that it still makes sense? It's still a binary search tree, so to say, so we can still have the property that the right child is always larger, the left child is always smaller, and so on. How can we do that? Now, in this case, it's pretty simple. It's just performing a so-called single right rotation. This is called a single right rotation. Single right rotation. A very simple thing that we need to do here. The only thing that we actually do is we rotate so that B becomes the root node and A becomes the right child of B. C remains the right child of A. And then one more thing that we do is we get E, which is the right child of B, and let it be the left child of A. So let me draw the tree once we have done the rotation here. So think about it. We rotate here. So B becomes the actual root node here. I just need to find the colors here. Sorry. So we have green and white. There you go. So we have B as a root node. Then the right child of B is A. Then C remains the right child of A. And now what we did is we said E is going to be the left child of A. Now this makes sense, of course, because think about it. E is obviously larger than B, but less than A. And if we put it to the right side of B, it's still larger than B and less than A. So we can do that without problems. And now the rest remains the same. So we have D here and F here. And this is how you rebalance this kind of tree, because now you have 0, 0, 0, you have -1, you have 0, and you have 0. So this is a perfectly balanced tree. We don't have any major unbalance here, and it's all done with a single right rotation by just rotating that. Now, this is not so simple at case B. We're going to look at that in a second, but now we can look at a very similar case, which is the case C, because here we only do this, we do the same thing, and the only difference is we perform a single left rotation. So single left rotation here, essentially the exact same procedure. Now we let C be the root node, A is the left child of C, D becomes the right child of A. We have the same logic here, so let's draw it out. We have C, C is the root node, then we have A, then we have D becomes the right child of A, because of course D is less than C, but still larger than A, so D is less than C, larger than A. Makes sense. Then we have B, and then we have E and F. And we can see that the balance is the same. We have 0, 0, 0. Here we have 1. Here we have 0 and 0. So case A and C are very similar and can be solved with a single right rotation or with a single left rotation. Now let us look at case B and D. The solution here is quite similar to case A and C, but we need an extra step in order to get there. Now, the first thing we want to do when we look at case B is we want to get it into the same structure that case A has. Why? Because now if I'm going to rotate here, so if I say rotate a single right rotation here, the problem is that I have E and F, and then I have problems because I would end up with a tree that is B, then I would have A, then I would have E, and then I would have F, and then I would have C, and then I would have D here. And the problem is then I'm, again, one more time unbalanced because I have 1 here, then 2 here, 3 here, so I have an unbalanced tree again. I cannot just go ahead and perform a single right rotation. So in order to make an efficient rebalancing on case B here, what I need to do is I need to first perform a single left rotation on the subtree. Even though it's balanced, we don't have any major unbalance here. But what we need to do is we need to rebalance, so to say, or at least it's not really rebalancing because it is balanced, but we're going to perform a single right rotation on B and E. So what we're going to do is we're going to, let me just do this up here. We're going to rotate here so that E becomes the root node of this subtree here, and B becomes the left child of E. So what we end up with is, I'm going to do it without colors now. We have A, and then we have E, and then we have B, and then we have D. Come on. Then we have D, and then we have F here. Or actually, do we have F here? We have, sorry, we don't have F here. We have F here. And then we have C here. And now we can see that this here, even though the letters are not exactly the same, this tree that we have up here after one left rotation is exactly case A. And now we can perform a single right rotation and get the same result that we got with case A. So this is called a double left right rotation. This is what we need to do in case B. We need to first go ahead, take this subtree here, rotate it, perform a single left rotation so that E is the root node, so that we end up with the same structure that we have in case A, and then we just perform another single right rotation on the root node here, so the same thing that we did for case A, and we end up with a rebalanced tree. So what we need to do here is just, again, to go ahead, E is the root node, A is the right child, F is the left child of A, and so on. Actually, the same thing that we did here, nothing too complex. And for case D, it's also not too complicated. Here we do the same thing, but first we rotate right, then we rotate left. So in this case, again, without any colors, A would be still a root node. Now here we would rotate D and C, so we would get D as the node here, then C as the node here, E as the node here, then we would get F here, and then we would get B here. And as you can see, this is the exact same structure that we had in case C, even though the letters differ, but it doesn't matter. And then what we do is we essentially just go ahead and rotate, do a single left rotation here, and we end up with a balanced tree once again. And this is called a double, come on, a double, obviously right left rotation. And this is how you solve all these different scenarios, all these different cases of unbalanced nodes. You're going to have unbalanced subtrees, you're going to have unbalanced tree as a whole, but wherever you find structures like this, you can solve them with single right rotation, single left rotation, double left right rotation, or double right left rotation. Last but not least, let's quickly mention why this is possible in logarithmic time, so why this is in O of log n. Obviously because the rotation itself can be done in constant time, and we will never ever have more rotations than we have levels. No matter what happens, we're never going to rebalance and have more operations, more rotations than we have levels. And the levels are in a balanced tree logarithmic, so whatever we do, whatever we end up with, we cannot rotate more times than there are levels, and the amount of levels is a maximum of logarithm 2 of n, logarithm base 2 of n, in a somewhat balanced tree. This is the case, and because of that, the rebalancing of a slight unbalance in the tree can be done in logarithmic time. And because of that, the rebalancing is done in logarithmic time, inserting into a balanced tree, logarithmic time, deleting from a balanced tree, logarithmic time, finding elements in a balanced tree, logarithmic time. And the moment you delete something or insert something, you might cause an unbalance, but the rebalancing itself is also logarithmic. So whatever we do, it's always going to be logarithmic. So that's it for today's video. I hope you enjoyed and hope you learned something. If so, let me know by hitting the like button and leaving a comment in the comment section down below. Also, make sure you subscribe to this channel in order to see more future videos for free. In the next video, we're going to talk about B trees, another kind of self-balancing trees. So stay tuned for that. And other than that, thank you very much for watching. See you in the next video, and bye.